Hi, I've just been prescribed Losartan, but I don't know anything about it.
No problem, I can talk you through it. What would you like to know?
I'd like to know, what is it and what is it used for? Why do I need it? How was it discovered and developed? What does it look like? Is this the only drug that does this? How is it made and how does it work? And are there any side effects?
Sure, let's go through these one by one. Losartan is an angiotensin II receptor antagonist, or known as ARB for short. According to the NICE guidelines, Losartan is used to treat hypertension, particularly in the elderly and people of Afro-Caribbean origins. It is also used for hypertension with intravascular depletion and diabetic nephropathy, as well as chronic heart failure.
Okay, but how does Losartan do this?
So normally, the renin-angiotensin-aldosterone system, or RAS for short, regulates blood pressure and helps in renal control of fluids and electrolyte balance.
How?
The liver releases angiotensinogen, a macroglobular precursor. This causes juxtaglomerular cells that are found in the wall lining of the distal tubes in the kidneys to release the enzyme renin. Renin then cleaves angiotensinogen and converts it to decapeptide angiotensin 1. Angiotensin converting enzyme, or ACE, is released by the lungs in response to the increased angiotensin 1 in the blood. ACE clips a dipeptide from angiotensin 1, creating angiotensin 2. In turn, angiotensin 2 then binds to the AT1 receptors, which causes vasoconstriction in the smooth muscle membrane and increases aldosterone secretion, which will increase sodium ion uptake and decrease potassium ion levels, therefore increasing blood pressure. However, when blood pressure is too high, Losartan interacts with this system by competitively inhibiting angiotensin 2 binding to the AT1 receptor. The binding of Losartan means that angiotensin 2 can no longer bind to the receptor, which causes a domino-style effect, leading to the inactivation of the G protein on this membrane, decreasing the production of inositol triphosphate IP3 and diacylglycerol DAG. This causes a reduction in intracellular calcium ions and the inactivation of the phosphokinase C enzyme. The calcium channel on the membrane then closes. This means that vasoconstriction is limited and less aldosterone is secreted. Sodium ion levels in the blood are reduced, and so this reduces blood pressure. The relative amount of potassium ions in the blood therefore increases, which is excreted via urine, stimulated by Losartan. The increase in flow of urine also promotes water loss from the blood, again decreasing blood pressure.
How was Losartan discovered and developed?
My colleague, who is a scientist, will explain more of the chemistry behind Losartan.
Takeda were initially trying to develop an anti-inflammatory drug, but they found an imidazole derivative which showed weak antihypertensive effects, for which they then released a patent. This molecule was known as S8307. DuPont was also a pharmaceutical company that was also trying to develop an antihypertensive drug. Using Takeda's knowledge of S8307, they further developed it by using computational chemistry. They added a carboxylic acid group as they realized they lacked multiple acidic functional groups when compared to angiotensin II, calling the new molecule EXP6155. However, even though it was 10 times more potent, it lacked oral availability. The potency was still not high enough, so EXP6803 was produced, which was larger and contained a benzamide. Potency was increased, but oral availability did not. EXP6803 was not lipophilic enough to pass cell membranes and enter the bloodstream, so needed to be modified again. DuPont recognized that the amide was responsible for this and subsequently removed it, creating a biphenyl structured compound, naming it EXP7111. The affinity was lowered, but it was now orally active. Replacement of the carboxylic acid group to a tetrazole group made it less polar, further increasing oral availability and increased duration of action. This final modification to the structure was named Losartan. DuPont and Merck merged and marketed this drug together.
Whoa! I never knew drug discovery was so complex.
Let's delve deeper and look at the structure of Losartan. Losartan is comprised of a tetrazole group, a biphenyl group, an imidazole, a chloro group, a hydroxymethyl group, and an alkyl side chain. Now, let's look at all the necessary binding interactions that occur. Due to the acidic nature of the hydroxymethyl group, hydrogen bonding occurs between losartan and the receptor. Ionic bonding occurs because of the tetrazole group. The alkyl side chain is hydrophobic and so binds to the receptor using van der Waals interactions.
There are 7 ARBs that commercially exist alongside losartan. These are azilsartan, candesartan, eprasartan, irbesartan, olmesartan, telmisartan, and valsartan. Here are all the groups that ionically bind. These are the groups that bind using van der Waals interactions. All of these groups bind with hydrogen bonding. And finally, these groups bind using pi-pi stacking interactions.
But how is losartan synthesized?
The initial process involved 10 steps and harsh conditions. This meant that the production of losartan was inefficient and expensive.
How is it made now?
It was developed to the current process, which involves the following 4 steps. In the first step, the imidazole group is formed using liquid ammonia at 65 to 70 degrees for 5 hours. The proton on the ring is then substituted for a chloro group using N-chlorosuccinimide to increase bioavailability. Then, the second step involved the formation of a substituted biphenyl derivative using almond biaryl synthesis using copper powder at 210 degrees for 2 hours, followed by NBS bromination. This reaction requires NBS and AIBN under reflux. The third step is the reaction between the imidazole group and the substituted biphenyl derivative, which forms 4-chloro-5-hydroxymethyl imidazole. However, this reaction forms a racemic mixture. Using liquid chromatography, these 2 isomers are separated. The desired isomer is isomer 2. The cyano group is then substituted for the tetrazole group. The reagents required for this reaction are sodium azide, dimethyl formamide, ammonium chloride, and potassium hydroxide. This is done at 100 degrees for 9 days. Now we have losartan.
So, when I take losartan, what happens in my body?
Approximately 14% of losartan is converted to its active metabolite, EXP3174, which is 10 to 40 times more potent than losartan. The active metabolite is a non-competitive antagonist to AT2. The hydroxymethyl group in losartan is oxidized to a carboxylic acid group by the isozymes CYP2C9 and CYP3A4. The metabolite works alongside its parent drug to exert its hypertensive effects. Now, we are going to compare the structure of losartan to angiotensin II. Losartan shows the following structural features with angiotensin II: the imidazole ring, the alkyl chain, the tetrazole ring that mimics the binding activity of 2 hydroxyl groups on AT2. We've already discussed how each functional group binds. Now let us look at how they bind to the amino acids contained in the AT1 receptor. Here's the AT1 receptor. As you can see, it consists of 7 helixes. The hydroxymethyl substituent on the imidazole ring to the 267th glycine in the chain. The biphenyl methyl group binds to the 206th phenylalanine. The tetrazole group binds to the 199th lysine. The alkyl side chain binds to the 198th threonine.
Are there any side effects that I should know about?
Due to losartan's specificity, vertigo is the only common side effect stated in the BNF. This is an off-target adverse effect, as losartan promotes greater flow of urine for its indication of lowering blood pressure. However, this loss of water alters the balance of fluid in the ears and therefore results in vertigo. The on-target adverse effects are as a result of losartan essentially working too well, resulting in symptoms of hypertension such as dizziness and lethargy. Angiotensin II antagonists are used as an alternative to ACE inhibitors because of the dry cough that patients experience when taking ACE inhibitors. Therefore, ARBs are used to abolish this adverse effect.
So just to make sure I've got it right, Losartan is used to treat hypertension, hypertension with intravascular depletion, diabetic nephropathy and chronic heart failure. It is designed to target the RAS system. DuPont developed Losartan, the first ARB drug. Losartan is made up of a tetrazole group, a biphenyl ring, an imidazole group, a chloro group, a hydroxymethyl group, and an alkyl chain. The commercial synthesis is a more efficient way of forming Losartan. Losartan is first converted to its active metabolite in the body, which attaches to the AT1 receptor on the allosteric site, and Losartan itself competitively inhibits the binding of AT2. It uses several types of binding interactions, including hydrogen bonding and van der Waals, in order to bind to the receptor. And finally, the off-target side effect of Losartan is vertigo, while its on-target side effects are symptoms of hypertension.
Yeah, you've got it. Do you have any more questions?
No, I feel well informed about my medication, thank you.
Thanks for watching!